Hello, everyone, and welcome back to Learning with Jelly. Today, we're going to go over a brief overview of statistical measures in Python. This is really beneficial for beginners in Python who are recently starting a course in college. You're trying to do some independent study, things of that nature. This is not an expert video, but today we're just going to touch the surface level of some statistical measures in Python to hopefully get you started. So, the first thing that we're going to talk about is the Numpy library. Okay, this provides us with arrays, and we're going to talk about the benefits over for having arrays versus lists. If you are new and you haven't watched the first video about Python data types, I highly recommend that you watch that. I'll link it in the description below. But pretty much, it's going to give us arrays, which are better informing a lot of operations, especially arithmetic operations such as addition, multiplying, doing conversions, things of that nature. So arrays versus lists, and we're going to hop into Jupyter Notebook that I've launched through Anaconda for you all. But pretty much, as I've already mentioned, you're able to form mathematical operations with arrays, unlike lists. And arrays is going to take up less memory, which is very beneficial if you're using big data in the world of data science. So let's hop over to the Jupyter Notebook and see some examples. So the first thing you want to do for this library is import it, okay? So we're importing NumPy as NP. NP is just an alias, so we don't have to keep typing NumPy every time we want to use a function from that package. So we're going to run that. And then here, let's do a list to remind you exactly what a list is. So remember, a list is enclosed in brackets, and I'm just going to have a numeric list of 1, 2, and 3. And now I'm going to try to add 3 to every item in this list. Okay. So I wanted to change from 1 to 4, 2 to 5, 3 to 6. Okay. So I want to add 3 to every item in this list. When I run it, Python gives me an error that says that you cannot concatenate a list. Okay. So, in order to add 3 to every item in a list, it's beneficial if we do an array. So, if I do another block underneath this, I can make an array. Let's just call that array. I'm going to call it array underscore y, actually. And now I'm going to do NP, which is the alias of the NumPy package. And that method is dot array. And in here, I'm going to have a list. So it's going to be parentheses, and I'm going to have the same 1, 2, 3 in that list format. Okay. Then I'm going to try to add 3 to that array. So array underscore y plus 3. And here we go. I get my desired output now, the 4, 5, and the 6. So a standard list in this example will not let us add to each element, which could be important. Say, for instance, you have a list of salaries at a company and you just want to iterate through those salaries using a for loop, and you want to multiply it by 0.02 for a 2% bonus for everyone, and you just want to spit it out. Arrays will be able to do that. A standard list will not. Okay. So it's very, very important in, like I said, mathematical operations. It takes up less memory. So this array in this NumPy library is very, very useful for us. Okay. So not only can you have a one-dimensional array, so what we have right here is just a one-dimensional array because we just have a standard list, one single list. You can have a multi-dimensional array, okay? And it gives us this type of structure where it looks like we have rows and columns, okay? And so let's look at that and try to create a multi-dimensional array. So I'm going to add a box underneath this, and I'm just going to call it multi underscore array. And I'm going to do np.array. And since I want to do a multi-dimensional array, I'm going to put brackets and then I'm going to have each of my lists in their own brackets. So another bracket, 1, 2, 3, comma, another bracket for the second list, 4, 5, 6. And then I'm going to print that out just by retyping what the variable is. And here I go. I have a multi-dimensional array. Okay. And we can see that it has 2 rows and 3 columns. So if we want to look at the shape of the array, we definitely can just do multi underscore array dot shape. And that's going to tell us that that is going to be 2 rows, 3 columns. Okay. And that's going to be beneficial once again if you're assigning data to more like a data set or data frame structure that we're going to talk about in a minute utilizing pandas. But pretty much, if you wanted to get a multi-dimensional array, that is how you do that in Python. Okay, so let's talk real briefly about pandas. So pandas, ooh, the pandas library. I just had panda. Pandas is a very, very, very popular data library. Okay, it's used for data analysis and data manipulations. One of the main uses of this is to convert those arrays that we just created into data frames. And this is very important because when those arrays transform into data frames, you're able to do a lot of cool things with pandas. You're able to get a .info that tells you everything that's in that data frame. You're able to get a list of the variables. You're able to see the top 5 rows, the bottom 5 rows. You're able to do a lot of data exploration when it's actually in a data frame. Pandas is also utilized to open up data sets. So if there's a CSV on your computer or a TXT file, you can utilize the Pandas library to do that. So let's look at pandas very briefly. And I get an example on the next slide that there are utilizing pandas in order to open up a CSV file, right? So let's go back and underneath this multiple array, let's import pandas. And a common alias that you'll see is PD so that we can utilize. And say, for instance, I already have it down here. I have a data set in my computer that's within the data folder of where I'm at in Jupyter Notebook. And then it's called cars.csv. So I'm actually going to read in this CSV file. Let me run the library. Okay. And now from this CSV file, I'm able to explore it. So I can do cars.head, which is going to show me the first 5 rows or 5 observations, better yet, of the data set. So then I can look at the top to see what the column names are, look at the bottom. I can also do a cars.info. Right, and it's going to tell me all of the column names. It's going to tell me how many are non-null. So since it tells me that I have 5,076 observations, I can look in these columns to see if any of these columns are missing, right? Because a number less than 5,076 would mean that there are some observations who have that missing value for that particular column. It's going to tell me what things are integers, what things are objects, what things are booleans, things of that nature, because we know with certain functions, they have to be of certain data type. Okay. So it could give me a lot of great information when I have it in this data frame structure. And you can see that the class is pandas.core.frame.dataframe. So it was able to read in this CSV file and automatically convert it to a data frame so that you can use methods like .head, .info, etc., to actually explore your data. And exploring your data is very important. Okay, so that's a brief example of pandas. So far we went through the Numpy library, which is that library for arrays is able to do a lot of mathematical operations that you once could not do with lists. And then we also went through Pandas, where it's able to convert things into data frames, including arrays and lists, and read in some of those raw data files that's on your computer. So both very, very important. Now let's actually get into some of the highlights and basics of statistics. So we're going to start with measures of central tendency. So I'm pretty sure quite a few you have heard of this before, but there are two main types of means. Okay, we know a mean is an average of values in a data set, right? So you add up all the values together and you divide it by the total number of observations. You have a sample mean, which is X bar, which is just going to be an X with a hat on top of it. You have a population mean, and it's denoted by this Greek symbol that I have highlighted here, and it's pronounced as mu. Both of these are calculated the same. So it's going to be that sum that I just mentioned, and you're going to divide that by the number of observations that you have, which most of the time is denoted by a capital N. However, most of the time you have a sample. You do not have the true population, okay? So most of the data that you will get is a sample of the truth, right? There's no way if you're doing a research on the amount of sleep that freshmen in colleges within the United States get. There's no way that you can survey every freshman in the United States that is currently in college and get their average sleep time per night, right? But you can have a data set where you can survey a sample of freshmen and then make inferences from that. Okay. So most of the time you have a sample of that true population. So let's look at some examples. And I ask you if it's a sample or population. So you surveyed 10 retirement homes to make an inference about the nation's retirement home conditions. That is going to be a sample, right? You weren't able to go through all of the retirement homes in the nation, but you did survey 10 of those. So you have a sample. So because that is a sample, you would be using X bar if you were to calculate that mean. You called 2,000 households to see how they would vote in the upcoming elections to determine the nation's next president. So you just called 2,000 households, right? You weren't able to call every household that is registered to vote in the nation, okay? So you have a sample of the population. You get 100% response rate from all of your employees to make conclusions about your company's working conditions. In this case, you would have a population because you're trying to make conclusions about your own job. You want to get responses from everybody in your company that is a population, not just one department, not just two departments. And since you do have 100% of employees that contribute their ideas, you are now working with the population in question. Okay, so a good review of sample versus population as it relates to mean. So we have that sample mean and that population mean. So outside of mean, what else do we have? We have median as well, right? So median is the exact middle location of a distribution. Why is median so important? Is because that is robust or non-sensitive to outliers. That is very, very important. So if you're working with data and you have outliers in your set, so say for instance, you are trying to work with data and you have the weight of everybody in your data set. And everybody in your data set is pretty much between the weight of 100 and let's say 280. And then you have a few outliers that are 400, 300 pounds. If you were to take the average of that, of course, your average would be high because those outliers are influencing that. But the median will not change. So if you have a ton of what we consider skewed data, which we'll talk about in other lessons, the median is what you would want to use. So, median or mean, visualize it. Okay. So, this is a distribution that we have, and this is pharmacy drug dispensing turnaround times as example data only. On the x axis, we have the time, and on the y, we have the frequency. And we see that it's pretty even. Okay. No symmetric. This is what we call it. No real true outliers. However, we look at the right and we see that the distribution of property sales, sale price, we see that we have a couple of homes that have some astronomical sales prices compared to what we consider the meat of the distribution. So, since this has outliers, should we use the median or the mean to best explain this distribution? And you're right. Either the median, and depending on the mode, may be your go to here for the distribution on the right. Whereas if you have a distribution that's equal or symmetric, the mean, median, and mode are all equal. So in this case, if the mean was 42 minutes, the median would be 42 minutes, the mode would be 42 minutes. Okay. So it wouldn't matter here with a symmetric distribution. But when you have outliers, the mean or the average would get increasingly larger because there are outliers. So go with the median and or mode depending on what questions you're trying to answer. All right, so we talked a little bit about outliers, but what can you do if there are outliers in the data set, especially if you're working with data analytics and data science in general? There's a few things that you can do for outliers. One is called median imputation, and we'll talk about that later on in later lessons, but pretty much you can impute the outlier to whatever the median is. So it's saying, hey, I have an outlier here that's about 95. The median here is going to be about 29. I'm going to change this outlier from 95 to 29. You can do quantile based flooring or capping. So, pretty much an example here is any value that's above the 90th percentile gets the 90th percentile value. So, if the 90th percentile value here was 44, this 95 would change to 44. You can transform the data, and we'll talk about that later on. But there are things like you can take the log of your response variables, things like that, to transform the data, and you can drop them. Now, don't go around just dropping a whole bunch of data, okay? Only if you truly know it is a data error, then you can drop them. Do not remove the data just because you want to make your analysis easier, okay? Because that could, in fact, be true data. So, for instance, what is a known error? So, say, for instance, I'm doing research on homes and properties, and I'm looking at the number of bedrooms in each home within a specific city. Now, I get data and it tells me that one of the bedrooms is 40. So within a family home, there's 40 bedrooms. Now, I clearly know that 40 bedrooms is clearly an error, right? Maybe they meant to put 4 and accidentally hit 0 before going to the next line. And so then I can drop that data point because that one is an error, right? So if you truly know that it is an error, you may drop them. But please, please, please do not go around just dropping data. Okay, so we talked about the mean and the median. Let's talk about dispersion. Okay, so we have a few things of dispersion that's important when starting with Python. So we have the absolute deviation, the variance, and the standard deviation. Okay, so your absolute deviation is the actual value minus the mean. And then your variance is going to take those deviations and they're going to square. Okay. Notice in variance that you lose your units. Okay. So, say for instance, I'm looking at sale prices of a home. Variance is going to give me dollars squared. And dollars squared mean nothing to me. Okay. That unit in itself, I know dollars, but I may not know dollars squared. Okay. And so that's why we came up, or statisticians better yet, with standard deviation. Okay. Which is just going to be the square root of the variance. And that way you're able to keep your units. So all of these tell us the spread of our data, how closely the data is together or how far apart it is. Okay. So when we're looking at variance, if the variance value is high, that means your data is spread apart from the mean. If it's low, that means your data is clustered around the mean. Variance itself is not a good measure to report to your company, to a business, because the units, so standard deviations is what we classically use. And when we talk about the empirical rule, things of that nature in future lessons, we'll know more about the standard deviation. But right now, just think of it as the spread of values within a data set. You can visualize it. So in this box plot here, the spread, okay, I see the minimum, the maximum, and I see what we consider the interquartile range, okay? And it's pretty symmetric. If this box moved towards the maximum, it will be pretty skewed. Or if it moved towards the minimum, it will be pretty skewed. So it is a pretty even spread, right, around the median, which in this case, since it's symmetric, the median is equal to the mean. And so that's how our data would look. Same thing if we go back to our old slide, right? This is a pretty even spread, whereas this one, some of the data is spread further apart, right? Okay. So outside of how the data is spread out, we can look at what we consider covariance and correlation, okay? How two variables actually vary together. And that's going to range from positive to negative infinity. Now, we're going to talk about covariance when it comes to reducing dimensions in your data set, which is very important for really complex data sets, things of that nature. But positive to negative infinity doesn't really tell us much. It doesn't tell us the magnitude on how these two variables relate. So there's correlation, right? It gives us a magnitude on how two variables relate to each other, how two numeric variables relate to each other. And it's called the Pearson correlation coefficient, and that's from -1 to 1, with -1 being strong negative correlation and 1 being a high positive correlation between two variables. Okay. There's different cutoffs, but for this presentation, we're going to use the cutoff of greater than 0.7. Those variables are considered highly correlated. So if two variables are highly correlated, what can you do? You can in turn drop one of those variables, making your analysis a little less complex. Okay. So let's look at that, right? So strong positive correlation. Right? This is an example. It's going up as one increases, as the x increases, the y also increases. So it's going in the same up direction on both axes. This is a weak positive correlation. This in turn is a negative correlation. As x increases, y decreases. So it's inverse if it's negative. And then no correlation at all. It's just going to be random points scattered all about. Okay. So that is correlation, and it can tell us a lot about two numeric variables. So very, very important to know correlation. So like I said, that is just a recap of statistical measures. Okay. Just very, very superficial. We went over the Numpy library. Okay. And that library is going to be for arrays. It's going to help us do mathematical operations. It's going to help us do conversions. We went through the Pandas library, and that is going to be great for data analysis and getting that data into a data frame structure so that you can analyze it. We've talked about the median versus the mean and how the median is more robust when you have outliers in your data set. And we also talked about what to do with those outliers, right? We don't just drop outliers just because we want to drop them. Okay. So there's different things that we can do. We also talked about dispersion or the spread of our data and how standard deviation is normally that go to talk about spread of data. And we talked about correlation of two numeric variables, right? What is negatively versus positively correlated, and what that actually means for us. So that is just a brief overview of some statistical measures in Python for those who are starting their journey in data analytics and or data science as a beginner. Thank you for tuning in. Please like, comment, and subscribe. And thank you very much.